Okay, welcome back everyone. So today we're starting part 5 of the ray tracing series. I've missed my daily release schedule. I was originally planning on doing daily, but it just turned out that life got in the way and work was really busy last week and all the other things that are happening in the world at the moment. So forgive me for being a bit late. We're going to keep cracking on though, and we're going to get to a point where we get a pretty interesting ray tracer by the end of this video. And we're going to start implementing the next two sections of the tutorial. So again, follow through on YouTube. I always link to this tutorial. It's called Ray Tracing in One Weekend. And we've worked our way through all the way up to diffuse materials. So we finished section 8 last time. So now what we're going to do is 9 and 10. And it's pretty ambitious. Implementing both these materials is a bit of work. But we're going to see how far we get. We're going to give it a good go. And if I need to break it into 2 videos, I will. But the idea is that we'll get sort of towards the end of the tutorial by in the next 2 videos, this one and then one more. So let's go and have a look at what we're implementing. If we actually reflect on what we did last time, we ended up with this diffuse material, Lambertian surface, which kind of is just scatters rays fairly randomly, and so it looks like a fairly matte surface. And we ended up with this ray tracer, and it was outputting this reasonably quickly. And so this was the code that we ended up writing. I won't go through all of it. If you want to catch up, look at the previous videos. But it probably does make sense to just try running it. So we'll run the release version of it, and we'll put it in data out. Make sure that we actually we're in the right directory. Okay, so that output that fairly quickly. And if we open recent, so that's what we get. Okay, and you can see that there's no light sources in this ray tracer. It's sort of globally illuminating, it's bouncing rays from the camera onto the surface that it can see. We're getting nice shadows and what have you. This is still low resolution though. And so what we're going to do is implement metals. That's the first thing. So there's a bit of extra refactoring that happens here, and then we also pull out what we've built already, and we put that in a class. Also, firstly, what we do is we build a material class, and then we define Hittable. I think we already defined Hittable. Oh, we added material property to the Hitrecord. Okay, and then we add that to the sphere class or the sphere module that we've already built. Then we end up building this Lambertian, I'm not sure how to pronounce that, Lambertian. Actually, let's find out. Lambertian, how do you pronounce it? Pronunciation. How to say Lambertian? Doesn't really help. Have a look. Why can't it give me a phonetic? Lambertian. It's really annoying. Because most dictionaries give you a kind of a phonetic thing. So the Free Dictionary Lambertian. Lambertia. Wow, isn't that a shame? It doesn't actually tell you how to pronounce the bloody thing without actually having an audio. Anyway, whatever, I'm going to call it Lambertian. And so, and I'll work it out later. So you build this Lambertian class, and then you end up building a reflect method, and that reflect method is used in the metal class. And it basically just smooth metals, you just do a pure reflection. Looks like a mirror. So we'll do that. Excuse me. and then we modify the sphere class. And we'll end up with something that looks like this, which is kind of starting to look pretty beautiful. And then we do some fuzz on that so that you end up with kind of like a textured metal surface, or at least you start blurring the reflection so it's not so clear. And then that's quite a bit of work, right? And then we'll do dielectrics. So dielectrics are basically, you know, things that implement refraction. So this is glass and diamonds and other things. So we'll end up building a refract function, and we'll build a dielectric class, and we'll end up doing building our spheres, and we'll have a dielectric and a metal sphere, which will look pretty cool. And so if we get all that done in the next hour and a bit, then we're doing pretty well. So let's have a look. We don't have a material class, and so what we're going to have to do is build one of those. And so what I'll do is create a brand new module here called material. Now the material class that they define here is again using abstract classes. And I've been through this, I've implemented this already a couple of days ago, and I spent a lot of time playing around with, do I do an abstract class? Do I think about, because the way that you do that in Rust is typically, at least my understanding is, you'd build a trait, and then you'd end up instantiating these trait objects. And so then you can effectively define or require certain methods get implemented. And I did it, and it worked, and it was quite complex. And then I had to think about it and did a bit more research, and I ended up building it differently. I ended up doing an enumeration instead. And so I'll show you what I ended up doing. I've got something like, it needs to be public, right? So, but I did pub enumeration, and then I called it material. And inside the material, there are going to be a number of enumerations, right? So we know about Lambertians already, which will have some properties. And then I wonder if I can get away with it doing it this way. I probably can. And then we'll have a metal material, and then we'll have a dielectric as well. Okay, so an enumeration in Rust is definitely more than just an enumeration in C. And so what we can actually do, and we'll sort of get to this later, but we'll end up building these enumerations and passing them around in our code to represent configuration for the material. So we'll instantiate things inside of these, like the material Lambertian enumeration, or that will actually have properties inside it, and then we'll be able to pass that around our code base. And it's, I think, probably going to be more efficient. I'm not sure, probably more efficient than building trait objects. At least I found that I started getting really deep into how the borrow checker thinks about, was it lifetimes, or was it the size of these things? So it seemed to get pretty complex pretty quickly. So we'll continue and try and build it this way. And so anyway, we have this material thing now, so that's good. Let's use it. So we'll add it to our main.rs file here. So this is our main program. So we'll add the mod. And then what we'll do is say we'll use material. Okay. Now, what we need inside of Hittable, so remember Hittable represented a trait that had a hit method, and that trait, that method would define whether or not something had been hit, and it would update that in the hit record, which was a mutable hit record struct that we pass to hit. What we need now inside of the hit record is the material. So we still need material here. Oh, and actually I need to implement that. So I need to include that. So we'll do use create material. If I can spell. Oh my goodness. All right, and then and so this thing will be a reference to a material enumeration. But we can't do default, so we'll get rid of this. Well, I guess we can get rid of that by let's just do derive default. It won't know how to do that. Yeah. I guess we could derive default, couldn't we? And we could make the default a okay, let's try that. So let's do implement default for material. What was it? Not default. My bad. Default for material. Okay, it was. Okay, and then function default returns, I guess it returns a material, and then it was just material. Let's do the default one will be Lambertian. Can I just return it that way? Clearly not. Oh, default returns self. Self kind : A. Okay, let's see what's the problem. Conflicting implementation. All right, let's just leave it at that for now. Okay, and so if we go back into Hittable, we've got a material property now, and then we also need to. What else do we need to do? The Hitrecord. Let's look over here. Stuff arguments into a struct, so it can send them to a group. When the color routine gets the Hitrecord, it can call member functions of the material pointer. Okay, sorry about the slurping noises. And so we need to go back to our object here, sphere. And sphere will have, it'll also have a material property here, which means that we need to use here as well. Yep. Okay. So that also means we need to pass in our constructor a reference to material. So we'll do that here, and then should be okay. So that now has a reference to the material that the sphere is made out of. We build that at constructor time, and then also we need to set that when we do when we implement the hit method. So we need to set what material was hit. So that's just going to be now, okay. Now what I want to do here is simplify. I want to simplify something. So what I did last time, if you remember, let's just kill this for now. What I did last time inside of Hittable was I made the struct public, but I kept all of the members private, and I built all these setters and getters. And that's fine, but I just don't like the amount of code that I've had to write there. And so what I'd like to do is kind of, I don't know if this is bad practice, it may be. I'm going to make all the members public, which means that I can kind of get rid of, I think, all of this. I don't really need that, I don't believe. And then when I go back here, I'm going to break a whole bunch of stuff. But when I go back to sphere, rather than doing, you know, rec set, I'm just going to basically do a, yeah. So what I'm going to do here, so if you remember, the Hittable method returned a Boolean to say whether or not something had been hit. And there's a better way of doing that, I believe. I don't know if it's going to be less performant, but there is a way of building something here, which is to use something called an option in Rust. And so an option in Rust is an enumeration. And what it does is it either has none, which is you know, there was nothing there, or some, and then you can do options on types. So we could do an option on a hit record here, and if we don't get a hit, we could return none, and if we do get a hit record, or if we do get a hit rather, we do intersect a array through that object, we can send back some hit record. And so that might be a nicer way of actually doing this. Whether it's less performant or not, quite possibly. I mean, I'd have to have a think about that. And so that's what I think I'd like to do. I've got sort of a number of places where I'm using that interface, and I'll need to go and update all of those areas. But I think that's something that would simplify things quite a lot. And so let's have a go at doing that. So I'm gonna do option hit record here. Now, so that's, I'm changing the type here. So hit record. And so the default would be none, right? So we could just do something like this. Okay, so that's simple. So the default trait is that it doesn't hit, it doesn't intersect. Oh, what's this? Lots of complaining going on here, but that's okay. And so the hittable list is going to have to change as well. The hittable list I think I can simplify this, because basically what it's doing is it's saying the hittable list is basically just a list of these boxed hittable records, if you remember. And the hittable is a trait object, which is why we have to have the din keyword here. And that all gets put on the heap, right? That's what box is basically doing. And so what hit does here is it basically takes it effectively it loops through everything in that vector of all the hittables, and then it calls hit. Now if it finds a hit, it just goes and sets a couple of things that we care about, like the closest, what is the closest hit so far, and then it returns. It was returning a Boolean, and so what we could do now is return the actual object, which is the hit record that it hit as part of that option. So I think that's doable. And so what I'll do is I'm going to change this. I don't believe I need a temp record anymore. Anyway, we'll see. So I've got closest so far, and so closest so far is still going to be starting from tmax, which we pass in. We don't need to hit anything, or if we do need to hit anything, what we could do is we could call it a hit record, and we could make it none by default. And that means that when we return hit record here, by default we're returning none, and that looks fine to me. And then in this loop, we're still loop through everything, but now the object is so it's still this boxed thing. So list, so for every object, we call hit, right? And the hit, oh, that's interesting. So what we don't need anymore is okay. So let's go back to Hittable. Right, so what we had in the hit method was a reference to this mutable hit record, and that was because we were updating the hit record every single time we found a hit, and that's pretty efficient. And so we're not passing things around by value that way. But this new way of doing things is going to return the option hit record. So we actually don't need a mutable reference in there anymore, and so that's certainly true in here. We don't need to have this mutable hit record. And so, but what that means though is that the hit object returns this option. Now, a way of finding out whether or not we got something in that option is to use this if let construct in Rust. So you can do something like this: if let sum record equals, and so the hit method still returns the option, and the sum here will basically destructure that enumeration. And if it's able to assign like this, then we know that we've got something. Otherwise, we know that we didn't get anything. So that's pretty cool, I think. And so, well, anyway, we're gonna try that, and then we don't need the hit anything flag anymore. We still do want closest so far. So, but the closest so far is going to be the record that is going to be rec.t, and t was a public member now because we changed that inside of Hittable. So that's a simpler, nicer kind of interface, I think. And then if we found something, then we just we update hit record to be whatever it was, right? Because all of the members are set when we return. So this is a fully built hit record, and so if we are able to destructure that enumeration, and if we're able to, if there was a record, if there was something inside of that, then we set that is the closest, and then we basically say that the hit record was some rec, and that means that if we never hit anything, then hit record will be none. If we do hit something, then we'll basically find the closest hit and return that here. So I think that's reasonably nice. And then if we go back to sphere, we can again get rid of this mutable record. We don't need it, and it doesn't satisfy the interface. We do need to return this option again here, right? And we also do need to change our return type, and so we can't just return false anymore. We by default will need to return none, because we want to assume that the default is not a hit. Now then, what we also need to do in here is change the way that we're doing this. So we still want rec. We still have rec, don't we? me just think about that for a sec. No, rec's not defined anymore. Right, so we need to construct a record in this case. And so this will be returning some, and then we'll create a brand new hit record. Okay. And then inside the hit record, we'll have a T, which will be temp. We'll have a P, which will be our pointer parameter. And then this will be temp. We'll have a normal, which will be whatever this thing was. Whoops, it's not right. Should still be the same. Right, this thing. And then hang on a second. What's r.p? rec.p set p. Okay. Well, we don't have that anymore. All right, let me stop and think about this better. So normal was rec.p minus center, and then all divided by the radius, right? In this case, rec.p is basically this. So it's basically r point at parameter temp. So in this case, we'll just do r point at parameter temp minus self center. So that's, I think, still right. We'll still we'll do that, and then we'll divide it by self dot radius. I think. Cool. I think that's right. And then the material will we need to set material, so that will be self dot material. And I think that's all we need here, I believe. Right, and so we'll do the same thing. It should be pretty much the same block, I believe. So temp, point at parameter temp, yeah, it's the same thing. Okay, so this has totally changed the implementation, but it's a bit clearer. I mean, we are constructing, so for Hittable, think about it, we're looping through everything. We do object.hit, so sphere.hit, so it's creating a whole new record every time, whereas before it was updating an existing record. So you could say this should be slower, but I'll keep it like this because I like the implementation, the interface. It's easy to think about. Anyway, so we've gone down that refactoring tunnel, and we've come back out. Got my T here. And so this is effectively what we were trying to implement, right? We were going through and updating the hit method here. And so we've done that. So that's good. Now what we need to do, I think that looks fine. Now what we need to do is build this Lambertian class. Now we're not going to do, we've decided, if we go back to our material, let's just see what's main's complaining about. Yep, so that's all changed now. So we'll go and update and fix this. Let's not worry about that for now. We just need to update this after the refactor. But so if we go back to material, what we did was do a material enumeration, and we built this default, which was the Lambertian material. And so actually, we're not going to implement this way, right? What we're doing is, what they're doing is building the scatter method, and they'll overload that. It's defined in that abstract class as well, up in here. Oh, that's not the abstract class, here. It's defined here as a virtual method in that abstract class. Right, so we don't want to do that. We want to have a scatter method in the material class, but what we're going to do is we're going to have, so we'll still have, you know, a public function called scatter, and we'll probably satisfy the same thing. So we'll the same sort of you know, signature. So we'll still have array in. So we'll still have let's just try and copy it for now. So it'll still be a reference to array, and we'll have a hit record as well, which will be a reference to a hit record. We'll have this new thing called attenuation, which will be a looks like it needs to be mutable. So we'll do, it's a reference to a mutable vec3, I guess. And then we'll still have scattered, which is a reference to array. Scattered. What does scattered do? Scattered gets updated as well. Okay, so that's the array that comes back out. So it's mutable as array. Yep. So we still have this kind of, let me get rid of this so we can actually see the full thing. So we still have the signature the same. But what we're going to do is and so what does it return? It returns bool, so we'll still do that. But what we're going to do is we're going to have one function here that will take also the material that it's that we're calling scatter for. So rather than implement it as a method on an object, or a method on a struct that implements a trait, which is kind of how we could have done it, what we're going to do is we'll pass in another thing here, and I'll put at the front called material, and this should just be a reference to a material. All right, let's go and fix this up. So we'll use create ray, use create hittable, hit record, use the vec one as well, use create vec3. Okay. All right, so now we have a scatter method, and what we're going to do we're going to use something in Rust called match, and we'll match on the material, right? Because we passed that in, and if it's it's going to be lowercase, and what we're going to do is we're going to say if we get a reference to Lambertian, then do this. And so this block of code is going to run if we match the Lambertian material. Now what's it complaining about? Right. Now this Lambertian class has a member called albedo. And so that's something we will pass in when we create it, when we create the enumeration. And it's going to be a vec3, right? Okay. And so that means down in here we need no idea what this means. Albedo. But then we'll need to pass in like a default vector or something. So I guess vec3 new. No. Can I do that? Vec3 default. Okay. Cool. So that should work. Now this thing also needs to match on albedo. Okay. And I also need to make sure that I get this right. And I will need to match on every single material type, I believe. Well, anyway, let's see what the compiler complains about here. Oh, lots of things. Field, not a method. Yep. Okay. It's not complaining so much about here, this implementation. And so what we're going to do is we're going to implement the material here. So so if we can if we get a match for material Lambertian and then this albedo member, then what we can do is implement it this way. So we'll say let target equal and I guess we'll just do let's call that rec. We'll say it's rec.p plus rec.normal plus random in unit sphere. And then we can do let scattered equal now this is ray times rec dot, well, we're passing rec and then target rec. Oh, target minus rec, target minus rec dot p. Okay, and then attenuation equals albedo. Oh. Scattered, hang on a second. So scattered is mutable. So we need to dereference it. Okay. So scattered is a reference to a array and a mutable one, and same with attenuation. It's a reference to a mutable vec3, and so we dereference those and set those here. My bad. All right, that looks fine. Oh, and then we need to return true. Okay, now what's going on here? Cannot find random in unit sphere. Okay. So we'd implemented random in unit sphere in main before, and I guess maybe we pull that into material now. So let's just do that for now. So yeah. Okay, so that will fix that. But then we also need the random number generator, and so to do that, we need to import the prelude here. So do that here. Okay, so that should just be the same, hopefully. All right, so let's go back to our sphere. Okay. So we've now got this enumeration that represents the material. We've got a default for it. We pass in the material to a scatter function that's going to just match on the material that's passed in, and we've implemented the scatter function for the Lambertian material this way. And I think that's pretty straightforward, isn't it? I don't even know if we need this match at the end, whether or not we'll get return false. Unreachable. Okay. Now what we want to do is let's go back and refactor this. This is starting to kill me. So main will fix main. Rec doesn't have these methods, but everything's accessible now. This is now in the material class. So it will be, well, actually, do we need? Sort of getting a bit ahead of myself here. So, we've sort of implemented this part where we're looking at the reflection, which is kind of going to be implementing the metal. But remember, we're sort of defining that we're hard coding the Lambertian sort of in here, and so. Okay, so we'll just jump ahead. So we've got world hit R, some other value which is not 0, which is a bit peculiar. The max and rec. We don't need rec. So we'll end up with we'll need, okay, so it looks like we need two more things here. We need let scattered, and that's going to be array. So it's ray. Can we do a default? I don't know if we derive default or not for array. No. So in that case, it's just going to be array, and then it'll be 3 vectors, and those vectors can just be defaults. Default. Okay, so that's scattered. Oh, apparently it's not scattered. Oh, it's only 2 vectors. The origin and the direction, remember? Okay. Now then we have attenuation. So let attenuation equal, and it's just a vec3 defaults. Now world hit isn't going to be isn't going to look like this anymore because hit returns the option hit record. So we'll do the if let again. So if let rec if let sum rec equal world. So this will define a record if it hits, and then what we've got here is depth. So we've got a new argument here called depth, which looks like it's an int. Okay, and so then we've got if depth is less than 50 and record.material. Okay. So this is where we do scatter. So we'll basically so when we don't just want material here. We're going to import the scatter function as well. And then what we can do is say scatter. And remember, the first thing was this reference to a material, so we'll pass in that. Now the next thing we needed for scatter was ray, record, attenuation, and scattered. So so the ray will be R, because that was passed in here to color. Then we'll have the hit record, which is going to be a reference to rec, and then we're going to have attenuation, I think, and then scattered. And so we'll pass in attenuation as a mutable, and then the same thing for scattered. Okay. So let's reflect. Oh, it's complaining. Oh no, it's fine. All right. So what we've got here is we've got this new thing called depth, and I think that's going to change how we recurse, or maybe not. No, it doesn't. Well, it sort of does actually. Yeah, it does. It changes how we recurse. Because when we call color again, we pass in depth +1, and so I guess we probably start with 0 and then we count up to 50. So we do 50 recursions, recursive calls. Anyway, and so then so if that's less than 50 and it scatters, and remember scatter could return false, and so if it scatters, then what we're going to do is go and return attenuation times by and call color again, this time with the scattered ray, the world again, and depth +1. Except this needs to be a reference from memory. The world needs to be a reference. Oh, it already is. Should be okay. Oh, what? Color. Okay. Color. Scattered. So reference to array, then we'll pass in world again, and then we'll add one to depth. This should be right. What's it saying? Mismatched types. Expected. Vec. Oh, is it because we haven't implemented vector times vector? Possible. It's weird that it would. So it's what have we implemented for vec? Have we got a vec times vec? Because attenuation's a vec and color obviously returns a vec as well. And so normally I would have expected it to complain about it on the operator, but let's have a look. So we've overloaded a bunch of these operators. We've got multiply for vec times f32 and float 32 times vec, and so I bet you that's what's happening, and that's why it's expecting a float 32 because it's matched vec. Okay, goodness gracious. All right, so we need what we need here is a new overload, and so this is implementing multiply for vec, where the type of the output is vec3, and self is going to be a vec3. Right hand side is going to be self, and we just do self output. Now in this case we're returning a new vector, and now the way that you multiply vectors should just be pairwise. So it should just be something like self.e0 times by right hand side .e0, and then self.e1, and so on, right? So we should just be able to be lazy and just copy do this, and then update each of the indices. So this is 1, this is 2, and that should be all we need. All right, and so then that fixes that, which is great. And then if we don't get this, then else we return this vector. I probably could just do default, couldn't I? But anyway. Okay, so that looks good, and then we don't need this anymore because we've basically got a better implementation of that. And this is our new color method function. Sorry, looks good to me. Do we need? We don't even need this, do we? So we can just do something as simple as that. So I think we're simplifying the code base a bit, which looks nice to me. Now let's go and find out where else it's broken. So sphere needs a material. All right, probably does. We'll fix that later. Now I know I'm jumping all around here, but let's go back and do implement the metal material type for scatter. So we're matching Lambertian there. Now we need this other thing called reflect. So we're assuming that we get perfect reflections off metal, which sounds reasonable. Why not? We're not doing constants, so we'll do V and N apparently. Okay, so V is going to be a reference to a vec3, and N will be the same. And it's going to return, I guess, a vector. And then we've got, what will it be? V minus 2 times by, now did I implement dot? Clearly not. See what I did there? Did implement dot. Okay, so we'll use that. So it's basically, it'll be vec3 dot times by n. That looks good to me, except of course it's complaining. All right, so this needs to be an integer. It needs to be a float. Now what else am I getting complaints about? This needs to be dereferenced, I guess. Or I could just pass by value, in which case these need to be references. Oops. But I mean, what we could do is just leave it like this. These are references, and then I dereference this way, I think. Should do the same thing. Cool, we can do it that way. Okay, and so then what we wanted to do was build this metal material, or in our case, it's going to be it's going to match on metal, and that's going to look like this. So it's going to have let reflected equal reflect of, so the unit vector in the direction and the normal for the ray. Okay. So R in ray in dot direction, and then whatever rect dot normal is. Let scattered equal ray rect dot p, and then reflected. And then, hang on a second, that's like this. And attenuation is going to equal Edo. Huh? Metal has this concept of albedo as well. Albedo vec3, which means we need to match here, which means that looks okay. And then we return, we return if vec3 dot of scattered direction greater than 0. What's it complaining about here? Okay, so reflect, oh, it needs references. Rec. Okay, ray, this also needs to be a reference. And dot, does it need to be a reference too? Guess so. Okay, references everywhere. Okay, so if that's greater than 0 as a float, then we're good. Okay, so that should implement metal for us. So what if we look at what this is doing? Technically, so we've got an incoming ray, and we've got the normal to the surface, and the reflected ray is going to be the incoming ray times by, minus 2 times the dot product of V and the normal times by the normal. And so the incoming ray is passed in to the scatter function. If we get we've got the hit record already, and we grab the normal for that. And so in this case, hit record is going to be like a sphere in this case, for example. it's not, is it? It's going to be its own material. Yeah, it's going to have a. Okay. Anyway, ignore what I just said there. And so then it's if and we get scattered. We say that scattered is the ray. So r dot p is the origin, reflected is the direction, attenuation is the albedo, and then we only return true if the dot product of the scattered direction and the normal is greater than 0. Okay, so that looks okay. Reasonably happy with that. So I think we can go back to main now. We've already updated our color record, our color function, so that's good. Now down in here we need to build a new sort of list of things, and so we had this vector of hittables, and we were putting spheres on there. It looks like we've got, how many did we put? 2. So it looks like we need 4. And so let's get this right. Let's build the first one. So hopefully you can sort of see that it's reasonably clear. So the first one is going to be the same sphere origin and width, but what we need here now is a material. It's a Lambertian, and albedo is a vector that's 0.8. If I can type 0.3 and then 0.3 again. Wow, that's some syntax, isn't it? Not so pleasant. Anyway, so that is the pattern we're going to follow. So that's 2, 3, and 4, and then we'll get rid of this one. So we've got all these spheres that we've defined. Color is we're gonna start from 0 here, and then the second sphere is going to be from minus 100.5 to minus 1. And it's going to be 100 wide, 100 big, in radius, I guess that was. And then we're going to have this new material, which is going to be 0.8, 0.0. Okay, now the next one is going to be 1, 0, minus 1, 0.5, 0.8, 0.6, 0.2. And then the next one is going to be minus 1, 0, minus 1, 0.5, 0.8, 0.8, 0.8. Okay. Now the other bit that we need, it's complaining here. Attenuation isn't declared as mutable. Good point. Okay. Now the other bit that we need is, okay, what's happening here? Match material. Dielectric not covered. Yes. So one of the cool things about Rust is that all the matches have to be exhaustive. So you can't end up with matching on an enumeration, for example, where you haven't implemented all of the different options. And so it's complaining at us, and so that's great. We'll do dielectric here, and the match is that it does nothing right now. So, okay, it just keeps the compiler happy, but it also means that hang on a second. I guess false. Yeah, that should be fine. Now sphere is also complaining. Can't move. Okay, material doesn't implement copy. Be great not to have to implement copy, to be honest. We'll do it for now. Derive copy, is that going to be enough? Or copy clone? Standard tray clone is not implemented for material. Yep. So you need, so you can have clone without copy, but you can't have copy without clone. And we need copy here. Okay. All right. Well, let's just do that for now. Okay. So that keeps that happy. Now, what we also needed down in our main function here was what is it saying it needs? I think we've already got it. I don't think that's new for us. So we still divide it by a number of samples. Yeah, cool. So I think we're good. So let's give that a go. Let's see what we get. So we'll do cargo run release, and then we'll put it in data out again. Let's see what we see in GIMP. Let's have a look. Okay. Oh, that's interesting. We haven't got the same reflective surface, which is pretty bizarre. I might just check what we created here in terms of our surfaces. So we've built these Lambertian surfaces, 0.3, 0.3, 0.3, 0.8, 0.8, 0.8, 0.62, 0.8, 0.8, 0.8, minus blah, blah, blah. That all looks fine. Looks okay, doesn't it? Maybe how did I implement the vector multiply? Did I get that embarrassingly wrong or something? So what did they do here? Yeah, it's just pairwise multiply, so that was okay. Multiply, looks good. Okay. So we've done something wrong. So what about the scatter function for Lambertian? So let's go back and check that. Well, it was metal, wasn't it? I think that, so that looks okay. It's the metal that's wrong. So let's just double check what we've done for metal. All right. These almost look just like matte surfaces, don't they? Oh, because I did create them as mattes. I did create them as Lambertian materials. It's a bit funny. Let's try that again. Whoops. All right. Let's see, this should look better. It should look different anyway. Definitely getting perfect reflections there. Looks pretty though, doesn't it? Starting to look like more of a real ray tracer. All right, so that looks pretty similar to what we should be getting. Now, I guess what they're saying down in here, if we also randomize the reflected direction by using a small sphere and choose a new endpoint for the ray. Cool. Okay, so rather than just doing the bigger the sphere, the fuzzier the reflections will be. This suggests adding a fuzziness parameter that is just the radius of the sphere. So 0 is no perturbation. The catch is that for big spheres or grazing rays, we may scatter below the surface. Is that right? So if this is the surface and the sphere is like this large, it's saying we could scatter down under here. We can just have the surface absorb those. We'll put a maximum of 1 on the radius of the sphere. Okay. All right, so what are we doing? Updating the metal. So for scatter, well they have a fuzz. All right, so we need a fuzz on the material. So metal has this other thing called fuzz, which looks like it's just a float. But that means down in here we need to match fuzz. And then what we can do is we can say if fuzz we'll do so so we need a default, right? So we'll do the default will be 1, and then we'll say if fuzz is less than 1, then we will say that f is equal to fuzz. Otherwise, f will just be 1, and that's what we end up with here. And so then, how do we use the fuzz? We change the scattered. So we grab a unit sphere. So we need to change this. So we have reflected stays the same, but then scattered is changed. And so scattered now has this concept of fuzz, which is fuzz times by f times by random in unit sphere, I guess. Complaining about cannot add to ray. Okay, should be okay then. Oh, that's inside. Oh gee, I'm an idiot. Sorry, so it's reflected plus that fuzz factor. Okay, Cool. So the ray that comes back comes from the same origin, but then goes back with this this sort of fuzz factor, and so I guess we'll get these more diffuse reflections, and so it should look like that. So what have we got now? We've got quite clear reflections. So let's try running this again. Missing fuzz. Okay. So we need to pass in a different amount of fuzz, I guess. 0.3 and 1. So we go back down here. And fuzz will be, for the first one, apparently 0.3. And then for the second one will be 1. Interesting. Okay, let's try that now. Let's see what change we see. Ooh, pretty. Yeah, so you can actually see a lot more fuzz on the silver one. So let's try reducing that. Huh. That's weird. Let's do 1. Oh, 0.3. Oh, so 1 was hang on a sec. Let me just try 0.3 on both. So 0.3 on both you get, okay, and then if I try 1 on both, yeah, you get a lot more diffuse kind of scattering going on. Okay, so I sort of like it. I like a little bit less than that. So let's, well, anyway, we'll go with 0.3 again, 0.3 and 1. Now what I'm going to do is we're still drawing this at a pretty low res, so I'm going to draw it a bit bigger than this. So we'll do 800. 800 by 400, which will be quite slow, I imagine, but let's just run it at a higher resolution. And I just want to see what it looks like, because we're still looking at fairly low res, and we get sort of these jaggy edges. So let's see what this looks like. Yeah, okay, nice. So that's starting to look quite pretty, isn't it? And we could do higher and higher resolutions, but it'll get quite a bit smaller, slower. So I really like that. It's beautiful. I think that's really cool. And let's just go 1 and 0.3. We'll render that again. So yeah, so I think, given how long this video has been, I might just stop it there. I think that's enough. I mean, it took a bit of time because we refactored, and I was a little bit slower today for some reason. What I'll do is I'll get the dielectrics video out tomorrow, and we can have a look at that in more detail. And this should be fun, because then we can start building some sort of, some other objects that do refraction, and we'll see some pretty cool kind of optical effects there. So let's have a look at our final render. Yeah, pretty. I think you'll agree that's pretty beautiful. So so we've got a gold and a silver metal sphere where we've got this fuzzy sort of reflection, which looks really beautiful. We've still got our Lambertian sort of matte surface in the middle. and the shadows being rendered appropriately, and it looks really nice. So look, thanks. We'll stop there. Please like the video if you liked it, and give me some constructive feedback. I know it was a bit slow after the last one, and I had a couple of people pinging me asking me where the next one was. So thank you firstly for watching and wanting to see the next one. And then follow along, right? We're putting it all the code in GitHub. I'll put a link below for the GitHub repository, and check the code out, start playing with it, see what you like. And thanks for joining this video. And the next one will come out tomorrow, so we'll get that done pretty quickly. Thanks heaps, and see you in the next video.